marginal satisfaction you get when you acquire one more unit. Okay, so we've been given a utility function. Remember, utility is satisfaction. Okay, so we are being asked to tabulate our marginal rate of substitution, which is the trade-off rate. Okay, how many of good y you need to give up in order to get good x. Okay. Yes. So the formula for the marginal rate of substitution here is the marginal utility of x over the marginal utility of y. So here we're dealing with partial derivatives, colleagues. Alright. So I'm going to illustrate to you how these partial derivatives work. Okay, so we have this utility function here. So the first thing is we need to get our marginal utility with x. Alright, so we have to derive this function with respect to good x. Okay. Now, one trick you should always remember for partial differentiation, okay, is if you are, like in this case, if you are deriving with respect to x, okay, any number that doesn't have an x disappears. Okay, because here we are partially deriving our utility function with respect to x. Okay, this is how you write it mathematically, like this first. Partially deriving this utility function with respect to x. So if any number doesn't have an x, it disappears. Okay, so the only thing we're going to derive is 4x. Okay, so if you remember deriving with the power rule, okay, 4x is like 4x to the power 1. So with differentiation, the exponent multiplied by the coefficient number in front of the letter, 1 times 4, that is 4. Then subtract a 1 from the exponent, 1 minus 1, that is 0. So you get 4x to the power 0. Now remember, anything to the power 0 is the same as 1, so you don't even need to write the 4x to the power 0. So our answer is 4. MUX equals 4. Any questions? Okay, next we're going to get the marginal utility for y, MUy. So it means we are deriving this function with respect to y, meaning anything that doesn't have a y disappears. So we're partially deriving our utility function with respect to y. Okay, so this 4x disappears. We remain with 6y. We need to derive 6y. So it's like 6y to the power 1. Remember, deriving exponent multiplied by coefficient number in front of the letter, 1 times 6, that is 6. Subtract a 1 from the exponent, 1 minus 1, 0. Okay, now we don't need to show y to the power 0. So we can find our marginal rate of substitution. Okay, so we're going to say MRS equals MUX over MUy x is MUX is 4, MUy is 6. We can simplify this fraction 2 over 3. Okay, so how we interpret this? This is how you interpret it. Say we are giving up 2 over 3 units of good y to get 1 unit of good x. Okay. Remember, marginal rate of substitution is the trade-off rate. So the trade-off rate is 2 over 3 units of y. Okay, if you want to get 1 unit of x, you give up 2 over 3 units of y. Just that it's a fraction, that's why it would be better if it was a whole number. Okay, but yeah, to get 1 unit of x, you give up 2 over 3, 2/3 of y. To get another unit of x, you have to give up another 2/3 of y. Okay. Now, if this trade-off rate starts to reduce, okay, from 2 over 3 it drops to now 1 over 3 and continues dropping. That's what we call diminishing marginal rate of substitution. It means the trade-off rate is starting to drop. Okay, but here we just calculated the trade-off rate. We're just saying you're giving up 2/3, 2 over 3 units of good y to get 1 unit of good x. Any questions? Okay, so these questions will come in different varieties, so I want to prepare you for any variety you're given, okay? Now, if you notice, the previous example, there was a plus sign and a minus sign. So, when you see a plus sign or a minus sign there, when doing the partial derivatives, those numbers that don't have the variable you are deriving, so they'll disappear. Now, in a case like this one here, okay, where the variables are attached to each other, we want to see what's going to happen as we do our partial differentiation. Okay, this is our utility function, x squared y cubed. Okay, so we have to get the marginal rate of substitution. So we derive this function with respect to x. Okay, partially derive. Okay. Now here, this y is attached to this x. Okay. So you can't just get rid of the y. Unless there was a plus or a minus sign, the y would have gone. But this y is attached to the x. So this is how we derive. We're only going to derive x, we just leave y as it is. Okay? And remember, deriving, multiply the exponent by the coefficient, so there's an invincible one here. Okay? Colleagues, in mathematics, they are invincible numbers. Okay? Here there's an invincible one. Okay? So 2 times this invincible one, you get 2. Then you subtract the 1 from the exponent. 2 minus 1, that is 1. So we get 2x to the power 1. Okay, then y stays as it is, y cubed. Now we're going to derive with respect to y. Okay, so the rules change. This time x will stay as it is, as x squared. Right. We'll derive y. So remember, exponent by the invincible number, 3 times 1, that is 3. X squared, and we have y here. Remember, subtract a 1 from the exponent. 3 minus 1, that is 2. So we get 3x squared y squared. Okay, colleagues? Yes. So our marginal rate of substitution MUX over MUY. Okay, so MUX is 2x y cubed. 2x y cubed. MUY 3x squared y squared 3x squared y squared. So colleagues, we need to simplify this, alright? Yes, so remember indices, alright? So let me put it here. So here we have x to the power 1, and here we have x to the power 2. When you're dividing same bases, basically same letters, you will subtract the exponents. Okay, so here you're just going to say, so we have 2 over 3 here. This 2 over 3 will stay the same. So you have x to the power 1 minus 2. Okay, because you're dividing the x's, so we subtract the exponents. Then y, you're going to say y to the power, we're subtracting this exponent 3 and this exponent 2, y to the power 3 minus 2. Okay, so our answer becomes 2 over 3 x 1 minus 2, that's x to the power negative 1. Y 3 minus 2, that's y to the power 1. Okay. So remember, negative exponents, they go to the denominator. Okay. So that x is going to go like this, 2 over 3x. And this y, it will attach it to this numerator here. So we have 2y over 3x. So that's how much of good y you need to give up to get good 1 unit of good x.